Okay, recording started already. Voice is being captured. So now we can start. Okay. I still haven't have the PPT loaded into this computer, but don't worry. I will just download the logs from the Moodle, and here we go. Okay. This one. Okay. This one. No, no. I will save it. Right click, save link as desktop. Good enough. Echo back. Please come in. Okay, please come in. Uh, because we have started the lecture already. Start talking about lecture already. So for the late coming students, okay, your attendance will be taken right after the your attendance will be taken right after this wait. Okay, your attendance will be taken right after this lecture. Okay, and let me do one more setting. Did will no, 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 not this one. This way, this way, this way. Okay. Wait. Okay, good. So last time we actually talked about the concept of a problem solving agent. Okay, okay. And we also talk about different kinds of agents. The first is called deterministic and fully observable problem. Okay, if we are having a deterministic and fully observable environment, then what we will have is a single state problem. And if we have a non-observable environment, then we will call it as a multi-state problem or conformant problem. And if we are talking about a non-deterministic or partially observable problem, we will call it as a contingency problem. Okay. And in this course, we will mainly focus on the single state problem. Okay, because or I would say is we will start with single state environment because it is far more easier to understand than the other problems. Okay. And essentially in a single state problem, okay, we have this, we actually define, okay, the configuration of the environment as state, okay, and essentially we actually consider the agent changing the environment as changing the state of the environment. Okay, okay. If we have taken, and this is so-called the single state problem. And one more thing I actually forget to talk about in the last lecture is that we also have so-called the exploration problem, where we don't even know what kinds of things are there in the environment. Okay, and the agent need to learn about what is happening in the environment where it is solving the problem as well. Okay, so this is called exploration problem. Okay, and in our course, okay, we will start off our discussion on single state environment. Okay, single state environment. Okay, so essentially when we are talking about single state environment, we are talking about an environment that is deterministic and fully observable, meaning that all the things, all the elements in the environment is fully observable by the agent. And when the agent makes an action, the changes made on the environment is only one. Okay. So whatever action is made by the agent on the environment in a deterministic environment, the changes will only cause one outcome. Okay. 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 So because of the nature of fully observable environment, that means that we have total vision of what is happening in the environment. So as a result, we can totally draw all the states, all the possible configuration of the environment out. Okay, we can totally list out all the possible configuration of the environment. And if we are using technical terms, we will say that we can list out all the states of the environment. Okay, because it is observable. Okay, because the environment is fully observable, meaning that we can just list out all the possible states of the problem. Okay, and one more thing is that because the action of the agent is also deterministic, meaning that every action that the agent perform will create only one outcome for each action. Okay, that means that we can actually just draw out, list out all the possible transitions of state caused by the action of the environment. So as based on these two observations, in fact, we can actually convert any single state problem into a diagram like this. Okay, in this diagram, in this network, okay, all the nodes, okay, are actually the states or a world configurations. Okay, okay, and all these configurations, okay, are connected to each other by arrows. And the arrows are actually referring to the transition between state to state. Okay, the environment is transiting from one state to another state. If, for example, here this environment, the environment or the top two environment on this diagram, okay, the left one is connected to the right one with the right with the arrow. Okay, that means that this environment can transit to the right environment. The left environment here, okay, the left environment here, okay, I'm lost. Can you see my mouse cursor? Can you see my mouse cursor? Okay, I try my best. Okay, okay. So as you can see here, the left environment, okay, the left state, okay, it is having arrow to the right state, meaning that the left state can transit to the right state. Okay, and this transition is actually caused by the agent moving from the left room to the right room. Okay, so in this example, you can see the transition between states to another state is caused by the action of the agent. Okay, so in a single state problem, we are given that a starting point configuration of the environment. We call it as the initial state. Okay, and our goal is to find a sequence of action that allows the whole environment to transit to the goal state. Okay, the goal state is the environment that we want the agent to convert to. Okay, we want the agent to transform the environment in a state that we want. Okay, and that state is called the goal state. Okay, but when we are talking about converting the environment to a desired configuration, then the agent would need to perform a bunch of actions on the environment to do the changes on the environment. So as a result, the solution to a single state problem is essentially figuring out a sequence of action that allows you to transit from the initial state to the goal state. Okay? 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 So you may ask a question is, Professor, so it still seems to be a little bit complicated. I really don't know what you are talking about the state, the goal state, and all these transitions. Okay, but are we actually solving problem in a flow like this? It seems that when I'm solving questions, I am not using the same flow to solve problem. But in fact, you actually is using a similar flow to solve problems in your daily life, okay? When you are doing mathematics, okay? It seems this way of solving problem is very difficult to understand, and it is not something that you never heard of. Okay, but in fact, I will give an example that illustrate that you actually solve problem in this manner, but you never realize it. Okay, so let me give you an example. Okay, so here is a mathematics question. Okay, in this question, it says that the farmer has 30 chickens and rabbits together. Okay, and there are only 100 legs. So you need to figure out the numbers of chickens and rabbits. Okay, this problem should be a question that you have seen when you are studying in secondary school. Okay, okay. This question is also commonly found when you are doing mathematics Olympics competitions in primary schools, I guess. Okay, so essentially this problem is actually trying to give you some configuration of the environment, and you being the agent need to figure out the numbers of chickens and rabbits that conform to the two conditions given. Okay, and to solve this problem, okay, we can actually take this attack. Okay, we can actually convert. You can actually pick a symbol that represents the number of chickens, and you can also pick a symbol that represents the numbers of rabbits. Okay, we know that from the description, we know that we cannot solve this problem with simple arithmetic, okay? But we can actually take a analytical approach, okay? The first thing we do is we try to eliminate extra details by converting number of chickens to a symbol called X and converting the number of rabbits to a symbol called Y. It makes us easier to convert the word description of these mathematical problems into mathematical equations. Okay, and the farmer has 30 chickens and rabbit together. For this condition, we'll write as x plus y equal to 30. Okay, the processes of converting the farmer has 30 chickens and rabbits together into x plus y equal to 30. We are actually eliminating certain details that is not necessary in the process of finding out the solution. Okay. And also, there are only 100 legs, okay? We write as 2x plus 4y equal to 100, okay? Because rabbit has 4 legs and chicken has 2 legs, okay? So we can write the relationship between the legs of the chickens and the legs of the rabbit in this equation, okay? X is the number of chickens, so we will use 2x to represent the number of legs of the chickens. And the rabbit has 4 legs, so we will use 4y this term to represent the number of legs of the rabbits, okay? And we add these two numbers together equal to 100. then we encode the sentences. There are only 100 legs into 2x plus 4y equal to 100. Okay. In this process, we are also eliminating unnecessary detail as well. Okay. We don't need to, for example, for the legs, okay, when we are consider how many legs are there, we don't consider the shape of the legs. We only consider the number of the legs. So the legs is literally being only the number of the legs is preserved in this representation, and all extra information are being removed. Okay, so this you have done this. You have done this conversion a lot in secondary school, right? 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 And this is essentially called abstraction. Okay? We try to remove unnecessary details and only keeps vital information. Okay? And essentially finding out the number of chickens and rabbits will be converted to finding the values of x and y. In this abstraction, we are converting a mathematical question with a lot of context into a simplified equation and symbols. Okay? Okay? So let's recall what we learned in chapter 1. Okay? Intelligent activities in either human or machines is achieved by the use of presenting significant aspects of a problem domain with simple patterns. We done so, we convert the number of chickens and the number of rabbits as x and y. Okay, and we also convert the range of description of the problem as sentences connected by symbols. Okay, as equation connected by symbol. Okay. And the next is we perform operation on these patterns to generate potential solution to the problem. Okay. And as you can see here, if you are being a human, the first thing you do is you would perform mathematical operations like this. Okay. The first thing you do is for the equation 1, you move the x to the right hand side. And then you put the y equal to 13 minus x into the equation 2, and then you rearrange the terms, and then you calculate the x value. Ultimately, for the equation 2, you are able to calculate the x value, and after you calculate x value, you put the x value back to the first equation, and then you get the y. Okay? As you can see here, when we are solving these problems, in the way secondary school students do, we are doing operations on those symbols we created in the first place. Okay, we are essentially conducting operations on the symbols and hopefully try to generate solutions. Okay, okay. And essentially, okay, this is the fastest sequence to get to the solution that we want. Okay, but you can just select the best move is because you have experience working with these equations. Okay. But what if you are a primary school student or a secondary school student who just learn about solving equation like this? You will probably make a lot of mistakes when you're solving the problem, right? You will make some move that you don't necessarily need to make, right? So although it seems that we can immediately get to the solution that we see here, but in real practice, okay, humans do need to think about what kinds of actions, what kinds of sequence of actions that will lead to the conclusions. Okay, we are just so used to solving this equation, we can immediately, through iteration, we know what procedure we need to do, okay? But if we don't have that iteration, then we may need to try more than once to get to the solution that you want, okay? For example, if students who are not so, who do not have a satisfactory performance in mathematics, okay? Maybe he cannot figure out this sequence so quickly. He will need to do more than one attempt, right? In that sense, that will be the third point, performing search, okay? Performing search to find the solution, okay? Okay. So in fact, you may think that Professor, why do people really map problem into symbols and perform operation on symbols and then do search? In fact, yes, you do this a lot in mathematics. Okay, you do this a lot in mathematics, but you do it intuitively and you are well trained that you don't actually realize you are doing this. Okay? Okay? Makes sense, right? Makes sense, right? All the things click in together, right? Okay? Then let's see how computer will solve problems, okay? So computers, if we want to program the computers to do all these sorts of operations, then it is too complicated to do, right? Too complicated to write one. So computer actually, we can actually program the computer to take another approach, okay? Instead of assigning the computer to try out different kinds of operation, I just let the computer to assign number to X and assign number to Y. Okay? Okay? Because we know that the total number of chickens and rabbits is equal to 30. So no matter how big the number of X and Y will be, the number will be from 1 to 30 or from 0 to 30. Okay? Okay? So we can just, okay, let the computer to try out all the possible combination of lump of integers between X and Y that add together can become 30. Okay? So we can try things like this, okay? We can actually first let the computer to assign numbers from 1 to 30 to X, and after that, for each value of X, for each X being assigned, then we assign the Y. Okay? So here we start off with a state that the X and the Y value are not being assigned. Okay? Okay. And then we try to assign a value to X. This assignment actually causes the change of the state. Okay. And as a result, we actually move to a new state. As you can see here, from this state to this state, the change of the state is caused by assigning one to the variable X. Okay. And one thing I actually didn't talk about it, but I think it's necessary to talk about it is that in this problem, okay, we actually model the states differently than humans, okay? In humans, the state is defined as the configuration of the two equations, okay? But in computers, we actually give up on letting computers to do all those sort of mathematics operations. We just let the computer to just try out all the possible values for X and Y. Okay, so because we try to let the computer just blindly test all the X and Y, okay, so in this situation, the state of the problem is simplified as value of X and value of Y. Okay, okay, okay. The reason why we have different representation of state in the computers versus human is that in humans, we are doing an analytical approach to solve the problem. Humans can actually do all these mathematical operation easily because humans have intuition. If you allow the computer to try out all the mathematical operation there is, it is even too tedious and too difficult to code. So instead for computers, we just let the computer to try out values of x and value of y. So in the computer, the state of the problem becomes the value of x and y rather than the configuration of the equations. Okay? Okay. So the state of the environment can be different if you are using different kinds of approach to solve the problem. Okay, okay. And as you can see here, we start off with a state that the x value and the y value are unknown. And then when we assign 1 to x, then it is transited to this state where the x is assigned to 1 and the y is not assigned to 1, is assigned to nothing. Okay. And then we assign 1 to y, okay, then we generate a state called the x equal to 1 and y equal to 1. Okay. And this can be a potential solution. Okay. And in this process, we list out all the possible potential solutions. And then each time a potential solution is being generated, we try it out. Okay, we try x equal to 1 and y equal to 1 on the equations that we established to see if this is a valid solution. Okay, if this is not a valid solution, then we continue. Okay, and right here, it reaches x equal to 10 and y equal to 20. So it stopped. Okay? 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 And as you can see here, when we are programming the computer to solve problem in this manner, we are essentially just letting the computer generate all the possible solutions and check it out one by one. Okay? So this behavior is the reason why we call this as a search. Okay? 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 So this is one thing that I hope every one of you can understand. Okay? In this chapter, when we are creating an AI to solve problem, we are actually creating a machine that do things like this. Okay? Generating all the potential solutions and then check it out one by one. And once a good solution is the real solution is reached, then we stop. Okay? Okay? So any questions? So any questions? Any questions? Okay, any questions? So the takeaway message here is that you need to understand humans and machines are operating differently when they are solving problems. Okay, I understand that most of you will think this method is still but for humans. If humans really solve problem in this manner, it is inefficient. But computer is good at doing tedious things like this, and it can do these kind of tedious things much faster than human. Okay? Okay? Okay. So this is how computer actually solve problems. Okay? Okay? So any questions? So any questions? Any questions? Any questions? And that is essentially the reason why we call this as a search. Okay, the computer doesn't have the intuition that humans have. Okay, it doesn't immediately jump to the conclusion. Okay, so computers essentially just list out all the solutions and pick the ones that is the real ones. Okay, okay, you need to understand this mindset such that you can understand the rest of these lecture notes and the algorithms that we learn in this course. So this is the reason why I spent so much effort to talk about this approach. Okay? Okay, so I ask again, does anyone have any questions about how computers solve problems? Okay, it seems easy enough to understand, right? Okay, so let's continue. Okay, one thing you must understand, okay, is that once we are able to convert the problem we are solving in a graph like this, then solving the problem is just as simple as finding a path that connects the initial state to the goal state. Okay? Okay? This is the one thing you must remember. Okay? At the end of the day, when we are trying to solve problems with computers using this approach, we are converting our problems into a network. Okay, and after we convert into a network, then the computer can just take this network and to find the solution for us. Okay, okay. In the previous example, we are also trying to convert the mathematical question in a network, okay? But the network is so huge that I don't have the time and the space, okay, to draw the whole network out. But you can see that this network is some sort like a tree, okay? Okay, okay. So any questions? Any questions? And as a result, okay, you may find that, especially for the student, okay, especially for the student who actually learn about, data structures, in other universities, okay, or other institutes, okay. If you have read, okay, if you have read textbooks about data structure, you will find that in many data structures textbook, they will talk about a data structure called the graph. Okay, and essentially, when we are talking about graph, we have algorithms that allow us to figure out a path from one node to another node. Okay, in essence, in this chapter, what we are trying to do is to convert the problem that we are having, that we aim to solve into a network like this, into a graph like this. Because it is now a graph, then we can use sophisticated and well-established graph algorithms to solve the problem. Okay, once we convert a single state problem into a graph like this, then essentially solving the problem is just finding a path that goes from initial state to the goal state. Okay, and because it is a graph, because the problem becomes finding a path from the initial state to the goal state, this is now solvable with standardized algorithms. Okay, okay, and this is essentially what we are trying to do in this whole lecture 3. Okay, okay. So any questions? Any questions? So you must remember the core essence of this approach is to transform the problem into a graph, okay? That the initial state and the goal state is the node in the graph. Once you achieve it, the rest of the problem becomes as simple as applying the standardized algorithm. Okay, and you actually have tried to do this in the past. Okay, in mathematics, when you're given a problem like this, okay, you will not try to just do any reasoning in order to figure out the number of x and y. Instead, you will not try to do some reasoning to try to do some deduction to deduce the number of chickens and rabbits just by looking at it. When you are seeing these kind of problems in mathematics, what you will do is you will convert these problems into a form like this, okay? And then you take this format, okay, and then you do mathematical operations to get the solution, okay? Converting a problem into a simpler form and then solve it with standardized technique is a thing that we humans do in mathematics. Okay? We are just doing the same in these lectures, but we are doing it with computers only. Okay? 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 You may think that I am really being too tedious and repeating myself, but the reason why I need to do things like this is highly abstract concepts, okay? And I want to make sure everyone get what I'm saying right now. Okay? Okay? So any question once again? Any questions? Any questions? And now let's take a look on how to define a single state problem. Okay? We actually need to define single state problem with 4 elements. Okay, that is the state, the successor function, the goal test, and the path course. Okay, so let's consider a more simple example first. Okay, imagine now you are enjoying your holidays in Romania. Okay, and you are in the a rack. Okay, I'm not sure how this is pronounced. Okay, I hope I do not pronounce it wrong. Okay, you are now located in the A city, or maybe I will say A city. Okay. Okay, this is the map of the Romania, and you are now located in this city. Okay, and you need to take a flight back home from Bucharest tomorrow. Okay, so imagine this is in Romania. Okay, you have booked a. Not every cities have a airport. Okay, so in order to leave Romania, you may need to transit back to Bucharest, and then you take the airplane there from the airport there. Okay, so as a result, now you are in the ACT right here, and then you will need to figure out a way to go to Bucharest right here. Okay, so you are now at this point. Okay, and you will need to figure out a path to go to this city. Okay, the Bucharest city. Okay, and this is the problem we are solving. Okay, and as you can see here, the distance between the ACT and Bucharest is very long, so there are many potential paths, many potential ways we can actually go to Bucharest. And the question that we want to solve is how to get to the Bucharest how to get to Bucharest if there is more than one path. Okay, yeah, from A to B. Okay, so if we just look at this city of Romania, okay, we have a lot of unnecessary detail. Okay, for example, the different region of the Romania is not that important for us. Okay, we just need to know where there are highway, where there are high-speed trains or other transportation that allow us to transit from one location to other in Romania, such that we can transit to Bucharest at the end. Okay. Other content, other information in this map is not necessary for us. Okay. For example, the region, how the administrative region is being divided in Romania is not a concern for us. We are only concerning where are the places that we can go to by transportation in Romania, okay, such that we can formulate a path, okay, that go from the ACT to Bucharest. Okay, so this map is actually having a lot of details we don't want to work with. So as a result, we try to convert into a simpler form. And in fact, this is what we do, okay? We are considering traveling from ACT to Bucharest. Traveling from ACT to Bucharest. So we only need to keep a look on the places that we can go to by transportation, by massive transportation that we have in Romania. So we just need to put the places down, okay? When we are traveling from one place to another, we are essentially modifying our location, okay? So the location become the state, okay? Okay, so here we are listing out all the locations that we can travel to with transportation. Okay, with for example with highway transportation. Okay, and these are the cities we can go to. So these cities are becoming the state of the problem. Okay, okay, and then the initial state is the ACT, and the goal state is Bucharest. Okay, okay, and then we have figured out the state already. The next thing is we need to also figure out how to transit from one state to other. Okay, and the action of transiting is we are driving from one city to other with through the highway. Okay, so as a result, we can draw a graph like this. Okay, we can actually draw a graph like this. Okay, in this graph, what we are having are the road network. Okay, that connect the cities together. Okay, they connect the cities together. Okay, so after we establish this graph, okay, then this problem becomes a graph problem. Okay, we no longer need to consider the technical details of Romania. Okay, we just use this graph and we can already figure out the path that we can go from the ACT to Bucharest. Okay, okay. So this is what we are talking about problem abstraction. Originally, we are working with a map of Romania, similar to everyone who are trying to find how to go from A to B with a map, okay? But this map is not necessary for us, okay? It has a lot of details that is not necessary for us to figure out a path from A to B, okay? The administrative region definition for Romania is not that important for us. Okay, we don't need to necessarily need to know where the boundaries of these two region of these two administrative region is for us to figure out a path between these two administrative region.
We only summarize the relevant information.
Yes.
The relevant one with the
Yes, we just toss away the unnecessary information. By doing so, by tossing out unnecessary information, we essentially convert the problem into a graph. Okay? And once we convert our problem into a graph, then it is something now the computers can solve it with standardized algorithms. Okay? Okay? And this is one thing you should also know as well. Converting a difficult problem to another problem and then solve it is a common technique in computer science and data science. Okay, so even though in the future you may not work on a problem like this, you should learn about this concept and then remember it in your mind. Okay, I don't know if you heard about a machine learning algorithm. There is a machine learning algorithm called SVM or support vector machines. Okay, and support vector machines is able to actually find a boundary between two different types of data points. Okay, but in some situations, in some problem, okay, it is not that easy to find a line or a plane that can separate two different kinds of data points. Okay, in some data set, okay, in some data set, the data samples are distributed in a manner that it is not that easy to find a plane, okay, find a line that can divide those two different kinds of data samples. Okay, so one possible technique is that you use some functions that transform the dimensions of the data points from a high dimension data point, from a high dimension domain, to a low dimension data set. Okay, then this would allow you to do the separation easier. Okay, and that method is so-called SVM kernel. Okay, yeah, SVM kernel. And the underlying principles of SVM kernel is the same as this one. We are converting one difficult problem to a simpler problem using transformation, okay, using some sort of data transformation, and then we solve the simpler form of the problem. Okay, okay, but here we would call this transformation as abstraction. Okay, okay. So any questions? Any questions? And sometimes, and also when you are building a graph like this, you will also need to conform. You will also need to conform with the reality. Okay? For example, if there is no line that go from the O city to the F city, to Odairus to the Pythagoras. Okay, I remember the pronunciation of these two words. Okay, the Odairus to the Pythagoras. Okay, so if there is no low network that connect the Odairus to Pythagoras, okay, then we definitely would not want to draw a line that connect them together. Okay, okay. So as a result, we should not draw a line from Odairus to Pythagoras in this graph. Okay, because it doesn't conform to the reality. Okay, and this is something you must need to remember when you are doing abstraction. Your abstraction should reflect the real situations. Okay, you should not oversimplify and toss out the necessary detail that will allow you, that will facilitate you to find a solution that is not realistic. Okay, okay. This is one thing you must remember. When you are doing abstraction, you must keep vital features. Otherwise, your solution will not be feasible in real world. Okay, okay. And essentially, we figure out this network by knowing what city is connected to which city through highways or through road networks. Okay, and we convert the connections information into a chart like this. Okay, and the one shown here is a portable solution. Okay, and essentially we can after we convert our map into a network like this, or into a graph like this, then we can actually figure out or finding a path that connect the initial state to the goal state. And here we are showing one of them. We can go to ACT, to the Cebu, to the Pythagoras, and then to the Bucharest. Okay, and this path is the traveling sequence that allow us to go to the ACT to Bucharest. Okay, okay. And this is a potential solution. And this is a potential solution that we can discover when we are after we do the abstraction. Okay? Okay. But sometimes knowing how to travel from ACT to Bucharest is not enough. We will also want to keep our cost down. Okay, so we can also include the cost traveling from one city to another, such that we can find the optimal solutions. Okay, okay. So for example, okay, most of you here must have traveled by MTR, right? Okay. And we can totally go from Prince Edward, okay, to Mong Kok by simply taking by taking the Tsuen Wan line, okay, to go from Prince Edward to Mong Kok, okay, as simple as one stop, okay. Although you can totally take a alternative route, okay, you can actually go to the Guangdong line, okay, and then go to the Hong Kong Island, and then you go back to Bangkok, okay, you go to the Guangdong line, okay, take a long loop and then go to the Hong Kong Islands, and then from the Hong Kong Islands you go to Mong Kok, okay, you can go in this route, okay? No one is saying that you cannot go from Prince Edward and then you take the Guangdong line to and then to go to the Hong Kong Islands, okay? And then you go from Hong Kong Islands back to the Mong Kok. You can totally take a loop, okay? You can totally take a loop, okay? Okay? Or you can also go from Prince Edward. You can take the Guangdong line to the Kowloon Tong, okay? And then once you reach Kowloon Tong, and then we will switch train, and then you go with the East Railway, okay, to go to the Mong Kok East Station, and then from Mong Kok East Station you walk to the Mong Kok Station, okay? You can totally do things like this, okay? And in the perspective of a graph problem like this, your solution works, okay? But it is just too time consuming. No one will actually take a route like this, okay? So when we are solving a problem like this, we sometimes would also want to find a path, okay, that have the least cost, okay, or a so-called the optimal solution, okay. In computer science and data science, the term optimal is dedicated to talk about the solution that is the best, okay, that is the best, okay. Whenever we want to say something is the best, then we say it is optimal, okay. That is why in our curriculum, we have a course called optimization. The term optimization is referring to finding out the best possible configuration of a solution of a problem. Okay, so next time when you see the term optimal, you will now know that it means the best solutions. Okay, and the cost of the solution is essentially just adding up the figures above the edges of the network. Okay, so essentially what we can do is we can actually just put the cost of going through one transition in the network. Okay, essentially in this network or in this graph, all the edges are representing the transition from one state to another state. Here, each edge is referring to moving from one city to other, okay? So to represent the cost of the movement, we can just put one figure right next to the edge, okay? The numbers that we put right next to the edge is actually representing the cost of the transitions, okay? Okay, and once we add this detail into a graph like this, then figuring out the cost from a state to another state is essentially just adding the numbers right at the end, okay? So we travel from ACT to Cebu, so the cost is 140, and we go from Cebu to Bucharest, the cost is 99, and when we go from Bucharest to Bucharest, the cost is 211, okay? So we add these three numbers together, and the cost of the solution will be 450, okay?
Minimize. We want to minimize the cost, right?
Yeah, so we want to minimize the cost. We can actually use some algorithms to achieve it, okay? But it will be discussed later. Okay. Okay. So now let's talk about how to well define a single state problem. Okay. So when you try to convert, okay, when you're trying to convert the verbal description of a problem into a single state problem, okay? Okay, you would need to define the following four things, okay? We'll first need to define the state, okay? The state is referring to the physical configuration of the environment, okay? You will also need to define the initial state and also the other state as well. Okay, one of the things that many students are doing wrong when they are doing the assignment is that or when they are trying to really form a single state problem is that when they are defining the state, they only define the initial state, but they do not describe how other state is defined. Okay, okay, okay. So when you are defining a state, you will need to define this manner. You will essentially to figure out what information should be kept that represent the change of the environment. Okay. Here we are figuring out how the agent move from one place to another. So the only thing that is changing is the location of the agent. Okay, is the location of the agent. So as a result, when we are defining the state of the environment here, we are defining the location of the agent as the state of the environment. Okay, okay, and let's get back to the data abstraction problem we have just talked about. Okay, when we are trying to we actually talk about this at the early section or at the early proportions of this lecture. Okay, and essentially what we are trying to do here is to convert the mathematical equation into simple like this, and then we solve it with computers. Okay, and when we are solving it with computers, what we are doing is we are trying to figure out x and y value that satisfy these two descriptions. Okay, so when we are solving this problem using computers, the thing that the computer is trying to figure out is the value of x and y, and we are trying to let the computer just assign values to x and y and let the computer generate all the possible configurations of x and y that at the end will satisfy the two conditions that is given in the questions. Okay, so in that sense, the only thing that the computer is changing in the environment is the value of x and the value of y. Okay, okay, okay. So here you can see the state of the environment is merely the value of x and the value of y, and that is the reason why here. Okay, because we are configuring the computer just enumerate all the possible solutions of x and y. Okay, and all the possible value of x and y, and then try out one by one. Okay, so in that sense, the value of x and the value of y is the only thing that is changing in this configuration. Okay, because x and y are the only thing that is changing in this configuration. So the state of this problem is now the value of x and the value of y. Okay, 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 makes sense, right? Makes sense, right? And the next thing, when we are working with single state problem, the next thing that we need to define is the successor function, okay? You may ask this, Professor, when we are defining the single state problem, we never define the network. Okay? I did not see anything called the graph or anything called the network here. But the issue is that, if I have a function that can automatically generate all the next possible states that the agent can go to, I don't need a network. Okay? So the next thing that we'll introduce is the successor function. The successor function, what it is trying to do is to take a state, okay? Take a state as the argument in the function Sx here. The x is the state, okay? And after taking a state as the argument, the successor function will return all the action that the agent can perform, and then all the states that the state will transit to after each action is being performed. Okay? Okay. If any state in the environment, I can have a function that I can use to generate all the potential neighbors that is connected to this state. Okay, then this successor function have already encapsulated all the whole structures of this network. Okay, okay. So let's consider this. If I have a function that given any city that I have here, the function is able to enumerate all the possible city right next to it. Okay? Then in essence, that function is representing this graph. Okay? Okay? So we are doing another layer of abstraction right here. Okay? Instead of hard coding the whole graph, into our problem, what we are trying to do is to write a function. This function will take the current state of the problem as the input and list out all the possible actions that the agent can do, and also what kinds of states that will be transited to after the action is being performed. Okay? If I have a function like this, then essentially what I'm having is, given a graph like this, okay, any city that I point to, I know what the neighbors are. Okay? Then this function would substantially be enough to encode all the knowledge, all the information in this graph. Okay? Okay? So in essence, with the successor function, you don't need to have the graph or you don't need to have the network. Okay? Because the successor function have already encapsulated all the things you need to learn about the network. Okay? Okay? So, any questions? Any questions? Any questions? And just for a bit, so I'm just folding a bit of extra information right here. Okay? So when you read the textbook of the data structure, or if you have friends studying in other universities in computer science or data science, okay, when they are studying data structure, they may actually learn graph. Okay, and when they are learning graph, okay, they would actually learn the graph can be represented as a formula like this. Okay, if you are given a graph, how you are going to represent is that I take all the nodes and I record its neighbors. Okay, I record all the nodes and I record all its neighbors. Okay, and this data structure is, so I remember it's called adjacent list. Okay, adjacent list or adjacent table. Okay, and essentially the successor function is doing the same as adjacent list, okay, in graph data structure, but we don't call it as adjacent list, we just call it as a successor function, okay? So any questions? Any questions? Any questions? So I don't know, I don't know where, I don't know whether you will refer to, whether you will refer to textbooks, more textbook on data structure on your daily, on your spare time, okay? So when you really take a look on graph in data structure, okay, they will actually tell you that we are representing the network structure of a graph by recording all the neighbors of each node in the network, and then we store the information of each node in a data structure. Okay? Okay? That thing is substantially the same as the successor function. Okay? Okay? The main difference is that when we are trying to solve a problem, we will also need to consider the actions that the agent need to do to transit from one state to another, okay? So the action information they have to be stored in successor function, but you don't see this information when you're working in graph in data structure, okay? So this is the major difference, okay? But substantially adjacent list is similar to successor function for what it does. Okay? Okay? So any questions? Any questions? Any questions? Any questions? Any questions? So now you understand how graph is being stored. Okay? How graph is being stored. Okay? When we are working with graph, the way we store is that we store all the possible nodes that appear in the network, and for all the nodes in the network, I store their neighbors. Okay, if I store all the neighbors, if I have a data structure that I can use to store all the neighbors of every node in the network, and I store this information for every node. Okay, then essentially what I have is something that represents this whole network. Okay? Okay? If I can find the neighbors of any node, and if the neighboring information of every node is being stored, then no matter what node I am in the network, I can find the neighbors, right? And that will be enough to represent the whole network. Okay? Okay? So in that sense, the successor function is doing the same, but it also provides the storage for actions. Okay? It also keeps track on what action that can cause a state go to another state. And this information is not being handled in regular data structure for graph. Okay? And that is the major difference. Okay? But all these are taught, I need to tell you this because I don't know whether you will actually take a look on graph in data structure in your spare time. And if I do not tell you this, you may get confused. Okay? But that is the major difference there. Okay? They are very similar, but they have substantial differences because they are solving different problems. Okay? Okay? And the next thing is called goal test. Okay? So when we are I've already talked about this in verbal terms, so I will not go through this. You can read at home, okay? It essentially means the same. Okay. And the next thing is goal state. Okay. Goal test. Goal test is the function that you can test whether the state is a goal state. Okay. Essentially, the solution is to find a sequence of action that goes from the initial state to the goal state. Okay, but we still haven't defined what is the goal state of our problem, and the goal state of our problem can be defined by a function that tests whether the state is a goal state. Okay. We can actually just check whether the state is equal to a particular state. For example, in the Romini Turing problem, we are very sure that the Bucharest state is the goal state. So we just check whether the agent is located in the Bucharest, and that is the end of the story. Okay? So this is called explicit goal state testing. Okay? But in some situations, okay, for example, in the mathematics question we just talked about, okay, what we are making the computer to do to solve this problem is that we let the computer to assign values to x and y and generate a list of solutions for testing. Okay, this is still in fact a single state problem, right? But the issue is that how we know the this solution that we generate is the goal state. How we know all the xy value, combination of xy value we generated here, which one is the real solution? Okay, the way we do is that we take the x and take the y, and then we put it back to these two equations to see if these two equations stands. Okay, okay. In that sense, the goal state is known by checking the state against a bunch of equations. Okay, doing computations. Okay, in that sense, we will call it as a implicit goal test. Okay, as a implicit goal test. Okay, we need to do computation in order to know whether that state is a goal test, and we'll call it as a implicit goal test. Okay, makes sense, right? And finally, we will also need to define the path course. Okay, essentially for all the actions that is available in successor function, we will also need to define its course as well. Okay, the course can be something you hard code, you just assign to it, or you may want to do computation to figure out the path, the step course, okay, for each step. Okay, okay. So any questions? Any questions? First of all, for the path course, you will need to define how each step course is calculated, and then you will need to define the path course as the summation of the step course, where the step course is the course of a single action. Okay? Okay? Any questions? Any questions? And then the rest, we will talk about model abstraction. Okay? We actually already talked about the concept of model abstraction here in this slide. Okay? Essentially, you have already do problem abstraction in mathematics. Okay? You remove unnecessary detail, keep the essence, and then solve problem in this simpler form. Okay? And the reason of doing abstraction is that without abstraction, we don't even know how to start solving this mathematical problem. We are able to solve this mathematical problem because we take an abstraction and convert into a system of equation, and then you use standardized system of equation technique to solve this equation. Okay? When we are doing abstraction for single state problem, we are doing the same. Okay? Okay? But we will need to remember the abstraction we are doing should conform to reality. We cannot oversimplify things such that our solution doesn't match with the reality. Okay? Okay? So for example, when we are simplifying this mathematical equation, we cannot just miss out any one of the equations here. Okay?
Must satisfy both. We cannot only satisfy one.
Yes. So this is what we are talking about realizability. Okay, we cannot oversimplify the questions. We should remove the technical details, but we should be reasonable about this process. Okay, so any questions? If there is no question, then this is probably a good time for us to stop today's lecture. Okay, I will put a stop on the recording, and because I already see other students are waiting